In this lesson, I want to talk about the interaction between lines in 2D and also in 3D. So in 2D, there are three possibilities. If you have two lines, they could intersect at that one point. That's the point of intersection. They could be parallel, in which case they don't intersect. Or they could be coincident. They could be the same line. And so there's an infinite number of intersection points all along that line. Now in 3D, there's actually a fourth possibility. So I want to talk about that. So in 3D, intersecting lines, for example, AB and BC intersect at the point B. Parallel lines, well, AB and EF, for example, are parallel, and they obviously won't intersect. AB and AB itself are going to be coincident, so that's coincident to itself. But then there's a fourth possibility of lines which are called skew. So AB and FG, they definitely will not intersect each other, but they are also not parallel because AB is going this way, FG is going that way, so they're called skew. Another example of skew lines would be AH and let's say FG. AH is on the front plane, FG is on the back, so they again will not intersect and they are also not parallel. So that's another scenario you have to deal with, and it's called skew. All right, show that L1, which is x equals negative 1 plus 2s, y equals 1 minus 2s, z equals 1 plus 4s, and L2, x equals 1 minus t, y equals t, z equals 3 minus 2t, are parallel, and implied is that they are not coincident, because coincident lines also have parallel direction vectors, but they happen to be the same line. So you have to make sure that they are not coincident by first of all showing that they're parallel and then checking that they aren't going to be right on top of each other. You'll notice also this first line, the parameter is s. The second line, the parameter is t. You got to make sure you have different parameters for the two lines. So to show that they are parallel and not coincident, I will first find their direction vectors. So v1, again, if these are the parametric equations, x equals, y equals, and z equals, I can read the coefficients of the parameter off, and that will give me my direction vector. So v1 is 2, negative 2, 4. And then v2, the direction vector for the second line, again, x equals, y equals, z equals. I can read the coefficients of t now, so negative 1, 1, negative 2. So I have v2 equals negative 1, 1, negative 2. Now to show that these two lines are parallel, I can show that their direction vectors are scalar multiples of each other. So basically by inspection here, I can tell that, notice, v1 is negative 2 times v2. If I multiply that by negative 2, I get that. So v1 is parallel to v2, but we still don't know that these lines are not coincident. So what that means is they're not exactly the same line. So to show that they are not coincident, what we're going to do is we're going to find a single point on one of those lines and show that that point can't be on the other line. Once we know that they don't have, if there's one particular point that's on one and not the other, they can't be identical lines. So the easiest thing to do is to pick, for example, s equals 0 and plug it in here to work out one of the points on line 1. So on line 1, x equals negative 1, y equals 1, and z equals 1 is a point. So now if I check that in line 2, so checking in line 2, so I would have negative 1 equals 1 minus t, 1 equals t, and 1 equals 3 minus 2t. And I try to solve each of these equations. So here I've already got 1 equals t. Let's just substitute that in. Sub 1 equals t into the x equation. And you're going to get negative 1 equals 1 minus 1 question mark, which is obviously false. So the 1 equals t didn't work with the x. It only worked with the y. Therefore, the point that we found here can't possibly be on the other line. So negative 1, 1, 1 is not on line 2. Therefore, the lines are not coincident. And since they are not coincident, but they have parallel direction vectors, they are parallel. So therefore L1 is parallel to L2. Now, it could have been that I found that these two vectors are parallel and that they were the same line, and I cannot then conclude that L1 is parallel to L2. So I had to go through this little rigmarole. It's not complicated, but you still have to do this to verify, hey, once I have parallel vectors, there's still two possibilities. I've got to make sure that the second one doesn't happen. All right, here we're asked to show that these two lines intersect, and then we're going to find the angle between them. So to show that they intersect, I would have to basically solve the equations. So for example, 1 minus t equals 1 plus 2u, that's equation x. T equals negative 1 minus u, that's equation y. And then 3 minus 2t equals 4 plus 3u, that's equation z. And now you'll notice I've got three equations with only two unknowns, t and u. So what I'm going to do is I'm going to pick any two of these, solve that system, and then verify that I can still make it work in the third one. If it only works in two of them but not in the third one, then the lines are not going to intersect. So here we go. I'm going to take this equation and this equation. I'm going to try to combine them. Basically, if I just add this to that right now, the t is going to cancel. So I'm just going to rewrite that y equation underneath. T equals negative 1 minus u. That's the y equation. I add them together. I get 1 equals u. Now that I have u, I got to find the t value. So let's substitute it back in. For example, t equals negative 1 minus u. That's the y equation. So negative 1 minus 1. So it's negative 2. So I've got u equals 1 and t equals negative 2 from the x and y equations. Now I need to verify that this also works in the z equation. So I'm going to verify in equation z. So I do 3 minus 2 times quantity negative 2 equals 4 plus 3 times 1 question mark. And if you check that, you do get 7 equals 7. So yes. So we now know t equals negative 2 and u equals 1 is where the two lines are going to intersect, but those are not the x, y, and z coordinates. So I got to plug one or the other, doesn't really matter. Let's go ahead and plug the u back in. So x equals 1 plus 2 times 1. Y equals negative 1 minus 1. And z equals 4 plus 3 times 1. So we end up with the point 3, negative 2, 7 is the point of intersection. Now we're asked to find the angle between the lines. Well, if I just do the angle between the two direction vectors, I'm all set. So the direction vectors are v1 is, again, it's just the coefficients. It's x equals y equals z equals. So negative 1, 1, negative 2. And v2 is, well, that's 2, negative 1, 3. So I use my dot product and cosine formula. So I need to do, first of all, v1 dot v2, which is going to be negative 2 minus 1 minus 6. I just multiplied these two together, and then these two together, and then these two together, and add them together. So it's going to be negative 9. And of course, the magnitude of v1 is also useful. It's a square root of, I'm going to do this in my head, it's going to be the square root of 6. And the magnitude of v2 is also useful. Again, I'm going to do that one in my head. That's going to be square root of 14. So now v1 dot v2 is going to equal magnitude of v1, magnitude of v2 times cosine theta. And so I'm going to plug in the v1 and the dot product value and the magnitudes and isolate cosine theta. So I'm going to get cosine theta equals, well, the dot product was negative 9, and the two magnitudes were root 6 and root 14, which is square root 84. And so theta is going to be cosine inverse of that. And I get approximately 169.1. Now, it didn't say whether it wanted the acute angle or the obtuse angle. We know that there's also, in this case, 10.9 is the acute angle between the two lines, but it didn't specify, so this is acceptable. All right, so now we're asked to show that L1 and L3, these two lines here, are skew and not parallel. So to show that they're skew, first we want to show they don't intersect. Once we know they don't intersect, they're either parallel or skew, and I can then argue that they're not parallel. So let's first try to solve. So that would mean -1 plus 2s equals 1 plus 2u. That's the x equation. 1 minus 2s equals -1 minus u is the y equation. And then 1 plus 4s equals 4 plus 3u is the z equation. I'm now going to try to solve the system. So if I take these two, I can eliminate s directly. So let's just do that. 1 minus 2s equals -1 minus u. That's the y equation. So I'm solving the x and y here, and I end up with 0 equals u. Now that I have 0 equals u, I can plug it, for example, back into the x equation. So I end up with -1 plus 2s equals 1 plus 2 times 0. In other words, if I add 1 to both sides, 2s equals 2. That means s equals 1. Okay, so the solution I got from using x and y was u equals 0, s equals 1. And my argument is that if I try to plug that into the z equation, something's going to go wrong. That way it's impossible for all three coordinates to match at the same time. So checking in z, we get 1 plus 4 times 1 equals 4 plus 3 times 0, question mark. And the answer is 5 does not equal 4. So the lines do not intersect. That's all we know so far. We don't know whether they're parallel or skew, but we do know they don't intersect, because we tried to solve the system and we're only able to solve 2 at a time. All 3 did not work at the same time. So now that we know they don't intersect, how do we know if they're skew? Well, we just got to make sure that they're not parallel. So V1, the vector direction vector for line 1, is 2, -2, 4. And V3, the direction vector for line 3, is 2, -1, 3. And you can see here that there is no k such that V1 equals k times V2. It's kind of obvious here. You could try solving it, but you'll find a problem because 2 and 2 are the same. So the only k that would work if it for x would be if k equals 1, but clearly the y's are not the same and the z's are not the same. So the fact that the x's are the same and the others two are not, we know that there is no k that works. So V1 is not parallel to V2. So the lines are skew, because either the lines were parallel or they were skew, and they're not parallel. So that's the only other option. All right, the last thing we're going to talk about is the shortest distance between two lines. And there's two scenarios that you have. Obviously, if the lines intersect or are coincident, well, the shortest distance is 0, so there's no point. But if the lines are parallel, then anywhere along those lines, you can pick a point on one line and find a perpendicular distance to the other one, and the distances will be the same the whole time. In fact, that's kind of what parallel means. So you pick any specific point on one line, so just make sure you get the numbers to work out, and then choose a generic point and xyz on the other line with the parameter involved, and then find the vector Pn and make it perpendicular to the direction vector of one of those lines, because they'll have the same direction vector, or at least a scalar multiple of each other, and then you'll be able to find n and then solve the magnitude of the vector. We've done this kind of thing before. We just have to add in the extra piece where you pick p on one line. So to do that, basically just pick a value of the parameter, doesn't matter. Pick 0 for the parameter, plug it in, and see what point pops out. And there's your first point on one line. Now, for the lines being skew, it's not quite as simple. Here is a diagram, and this line here and this line here do not intersect here. There's some space in 3 dimensions between them. So what you need is a point on one line and on the other that matches in such a way that if I make the connection between those 2 points, P and N, they are perpendicular on both spots, on one line and on the other. There's only one pair of points that will do that. So you can't just pick a specific point for one and then try to find the other. You actually do not know either of those points. So instead what you do is you put generic points x, y, z, and you have parameters involved for the p and for the n on each line. And you find a vector that's perpendicular to both direction vectors, so the vector for the blue line and the vector for the red line, the direction vectors. You do a cross product of those two vectors. They are not parallel vectors because otherwise that would have been this scenario. So they will have a cross product, and that new cross product is perpendicular to both of them. So it's going to be parallel to the segment Pn that you're trying to find. So once you have whatever that vector is, it'll be numerical. You know that Pn is going to be parallel to that numerical vector that you found from the cross product, and then you'll have a system of equations you can solve, and you'll be able to find both the location of P and the location of N, and then do the shortest distance of the magnitude of Pn. So let's do an example of that one. Find the distance between these two skew lines. This one's given in parametric form, but this one is not. So what I'm going to do is I'm going to make it into parametric form first because that's the only way that it works. So I'm going to basically set each of these equal to a new parameter. I can't use t because it was the one that used in that one. So let's use s. So I'm going to call this one L1 and I'm going to call this one L2. And so L2 now I'm saying basically 3 minus x equals s. Y plus 1 over 2 equals s, and 4 minus z equals s. And then I solve each of them for x, y, and z. So I subtract 3 and divide by -1. So x equals 3 minus s. And here I multiply by 2 and subtract 1. So y equals 2s minus 1. And then I subtract 4 and then divide by -1. So z equals 4 minus s. And so that is the parametric equations for line 2, and these are the parametric equations for line 1. Now, we already know they are skew lines, so we don't have to verify that. We're just going to take that for granted. So what we need to do is we need to find 2 points, and I know I've been calling them P and N, but those are just arbitrary names. So let's call them A and B. So point A is on line on L1, and it's arbitrary, so it has coordinates t, comma, 1 minus t, comma, 2 plus t, right? Because it's going to be one of the points along that line. It has to satisfy that. Point B is on line 2. So it has coordinates 3 minus s, 2s minus 1, and 4 minus s. So I need to find a vector that goes from A to B, or B to A, doesn't really matter. So I'm going to do vector AB, so here it is, vector AB is going to equal, it's going to be B minus A, remember, so it's 3 minus S, and then minus T, 2S minus 1, and then minus the 1 minus T, so it's minus 1, and then plus T, and then 4 minus S, and then minus the 2 plus T, so it's minus 2, and then minus T, and I'm going to simplify that a little bit. So it's 3 minus S minus T, and the next one is 2S minus 2 plus t, and the last one is 2 minus s minus t. So that's vector AB. Now we also need to find another vector that's perpendicular to the two lines. So I'm going to use this, the parametric equations of this line and the parametric equation of the other line to work out what the direction vectors are. And then when I do the cross product of those two direction vectors, that creates a new vector that's perpendicular to both of those lines and therefore parallel to the line, the vector I'm looking for, the AB vector. So V1 is, let's see, 1, -1, 1 is the direction vector for line 1. And then V2, again, it has to be written in the x equals y equals z equals version. Can't read it off of here. -1, 2, -1. And so to get a new vector that's perpendicular to other vectors in 3 dimensions, you use a cross product. So I need to find V1 cross V2. V2 cross V1 would have been just fine, but I'm going to do this one. So I hat, j hat, k hat, 1, -1, 1, -1, 2, -1. And then I'm doing the determinant of that. So I hat times the determinant of -1, 1, 2, -1, minus j hat times the determinant of 1, 1, -1, -1, plus k hat times the determinant of 1, -1, -1, 2. So if I keep this thing going, I have I hat times, and then negative 1 times negative 1 is 1, and then minus 2, minus j hat times negative 1, and then minus negative 1, so plus 1, it's going to turn to 0. That's convenient. Plus k hat, and then 2 minus 1. So this becomes negative I hat plus k hat. Or in other words, negative 1, 0, 1. So what we want now is for this vector here, AB, to be parallel to this vector here, which was the cross product. So I'm going to copy this vector and this vector onto the next slide in order to keep going. So again, I copied these two relevant vectors, the vector AB and the vector V1 cross V2. And remember, what I want is for them to be parallel. So if AB vector is parallel to V1 cross V2 vector, then there exists, and I'm not going to use K here because K hat was used earlier, but it's okay, it's not the end of the world. I'm going to use H in R such that, well, the rule is that they have to be scalar multiples. So 3 minus S minus T, 2S minus 2 plus T, 2 minus S minus T is going to equal H times the negative 1, 0, 1. So when I put that together, I get three equations. 3 minus S minus T equals negative H. So that's my X equation. And then 2S minus 2 plus T equals 0 is my Y equation. And then 2 minus S minus T equals H, that's my Z equation. And now notice here that this equation does not involve H. So really the best thing to do is to use equations X and Z and eliminate H and then combine it with equation Y. So let's just do that. Recopy equations X and Z. 3 minus S minus T equals negative H is the X equation. And 2 minus S minus T equals H is the Z equation. And when I add these together, I get 5 minus 2S minus 2T equals 0. And that's, let's call it equation 4. Since it's the fourth equation, I know the others were not numbered, but anyway. So I'm going to combine this one now with this one. So basically I can eliminate S directly by just adding these two together. So if I just recopy, let me write it this way, negative 2 plus 2S plus T equals 0. That was equation Y. So that allows me to get 3 minus T equals 0, which of course means that T equals 3. And I can plug that T equals 3 back in, let's say, over here might be okay. So I get negative 2 plus 2S plus 3 equals 0. That means that 2S plus 1 equals 0. So S equals negative 1/2. So what I've done now is I figured out the T value and the S value for the vector AB here, so I can plug these two numbers in here to get the vector AB. So AB vector is going to be 3 minus negative 1/2 minus 3, and then 2 times negative 1/2 minus 2 plus 3, and then 2 minus negative 1/2 minus 3. And when you simplify that, you end up with the vector 1/2, 0, negative 1/2. Now remember, the vector AB is the vector taking me from the relevant point on the first line to the relevant point on the second line, so that segment AB is perpendicular to both lines. So it's going to give me the distance between the two lines, the shortest distance. So if I do the magnitude of this vector, I've got my answer. So the magnitude of AB vector is going to be square root of 1/2 squared plus 0 squared plus negative 1/2 squared, which ends up being the square root of 1/4 plus 1/4, which of course is the square root of 2/4, which I will then simplify as the square root of 2, and then over 2. So the distance between these two lines now is the square root of 2 over 2. And that's the end of the lesson.